welcome. Now we will extend our ideas on the natural numbers, say ideas about a group, so that we can actually extend the natural numbers. That is, the reason we want to extend the natural numbers is to introduce inverses or inverse operations to addition and multiplication as far as we can. However, before we do that, on the natural numbers, let's consider a more abstract idea, namely with the idea of a group. A group is defined to be a set G with a specified element 1 in G, and an operation that associates to any pair of elements in G another element in G. Namely, for elements A and B, we have the element A times B. This operation should satisfy the following three laws: the associative law, the identity law, and the inverse law. These associative matches as before. The identity law is satisfied by the element 1, and the inverse law is where we want to head with our natural numbers. The element 1 is called the identity of the group, and the element A inverse is called the inverse of the element A in G. Additionally, a group is said to be abelian, or a commutative group, if it satisfies the commutative law, namely that A times B is equal to B times A for all A and B in G. We'll note that a group may consist of either finitely many or infinitely many elements. For a finite group, the cardinality of the group is called the order of the group, but additionally, confusingly, an element A of a group is said to have order n if A to the n is equal to 1, where 1 is the identity of the group. Just as is the case in the natural numbers, we often make writing A times B a little easier by writing AB instead of A times B. And we usually drop parentheses when the meaning is clear. Thankfully, the cancellation law holds in any group that if A times B is equal to A times C for some A, B, C, and G, then B is equal to A inverse A times B, so it's A inverse times A times B by associativity, so it's A inverse times A times C, so it's A inverse times A, again by associativity, so it's just C. Although it's really common to use multiplication notation, there are some cases where additive notation is used instead, and in the additive notation, the group operation is written as A plus B instead of A times B. And we have the exact same laws as before, since we still want it to be a group, just writing the operation slightly differently. The simplest group consists of a single element 1, with the group operation 1 times 1 is 1. This is not really an interesting example, but it does show you the most basic example. A more interesting example of a group is the symmetric group S of A on a set A, which is a set of all bijective mappings from A to A, where the product F dot G of two bijections is the composition of them, and the identity element of the group S of A is the identity mapping iota from A to A, which is that iota of A is equal to A for all A in A. And the inverse of any mapping in this group is just the usual inverse mapping. It's not hard to verify that S of A does satisfy the laws of a group. And so we have a non-trivial example. However, we can do even more interesting than the groups of bijective mappings by considering only those bijective mappings that preserve some additional structure on set A. These are called groups of symmetries on these sets. For instance, if we consider just normal geometry case, we suppose that a set A is a plane rectangle, and we consider Euclidean motions on it, namely any mappings that send the rectangle to itself. An easy one of this is the identity mapping, which is just leaving the rectangle alone. Another one is the flip, which will denote A, of the plane around the horizontal axis of the rectangle. This is a mapping that interchanges the vertices 1 and 4, and interchanges the vertices 2 and 3. Another similar one is the flip B around the vertical axis of the rectangle. And we note that if we repeat any of these two twice, we get back our identity element, namely leaving it alone. If we instead perform the flip A and then the flip B, we can interchange vertices 1 and 3 and 2 and 4. This amounts to a rotation, which we will call C, which we will note is the product of B times A. And we can also note that this rotation is a rotation of the plane around the center of the rectangle through an angle of pi. We'll also note that if we perform the two flips in the other order, we get the same rotation, namely C is also equal to A times B. These symmetries form a group of order 4 since there are 4 possible elements, 1, A, B, and C. As an example, we can write up the Cayley table of this group, namely when we consider all the multiplications of the group. That's shown here, and we'll see everything we've said is true, namely that A times B is C, that B times A is C, and we also have all the other symmetries we noted before. There are other finite groups, and we will note that on a Cayley table, though, before we consider for any finite group, and in fact possibly for infinite groups, that a group is abelian if and only if the Cayley table of that group is symmetric about the main diagonal, because that means that A times B is equal to B times A for all A and B. Also note how rows and tables are treated in the Cayley table, and the ordering that means for the product of the group. From here, we will note that in a Cayley table, each row and each column must be a list of all the elements of the group with no repetitions, because the multiplication of the elements of a group by a fixed element A is a bijective mapping from the group to itself. If we'll remember the previous table, the entries along the principal diagonals are all 1, reflecting the fact that every element in this group has order 2, namely that for any element, that element squared is equal to 1. There's another group of 4 symmetries, namely the group B of symmetries of a rectangle is thus a group of order 4, each of which has elements of order 2, and it's called Klein's Ware group. There's another group of order 4, which is the group of rotations that preserve a square in the plane. This group consists of the identity mapping, a counterclockwise rotation of pi over 2 radians, which we'll call A counterclockwise rotation B of pi radians, which we'll call B, and a counterclockwise rotation of 3 pi over 2 radians, which we'll call C. These operations satisfy that A squared is equal to B, A cubed equals C, and A to the 4th equals 1. So we consider this group as consisting of the products A squared, A cubed, and A fourth, where A to the 4th is equal to 1. This group is called Z mod 4. It's called the cyclic group of order 4. And its Cayley table is given here. We will note that it obeys all the rules we wanted. And additionally, we will note that since it is symmetric about the main diagonal, it is a abelian group. Additionally, one difference between this and the previous is that by considering these two tables, that the two groups are quite distinct, because every element of the first group is of order 2, but in this case, not every element is of order 2. Namely, consider A times A squared, we get B, not that A. In fact, the element A is of order 4, as you know A to the 4th is equal to 1. Thank you, that's all about groups for now. And next we will consider subgroups and homomorphisms. Thank you for watching.